All right, so we were doing a simulation to decide if more couples kissed to the right, and we had a sample proportion of 0.669, and we are testing to see if it's plausible that that is because of sampling variability. So what we've done is we have done a simulation, and we have that the number 1 represented kissing to the right and 0 represented kissing to the left. And I did actually, I did another trial. So I've done 1, 2, 3, 4, 5 trials, and I got that all the trials were, I changed them all into decimals. So my last trial was actually at 60%. So the question I'm asking based on this is, what is the probability that my p-hat is greater than 0.669? So what is the probability that p-hat is greater than 0.669? And based on my samples, out of my 1, 2, 3, 4, 5 samples, none of them, 0 out of the 5 samples that I took, simulations that I did, had a probability of greater than 0.669. So the probability that I get a sample statistic greater than 0.669 due to sampling variability is 0. Okay, 0. All right. So on to the next page. How do we make a conclusion? How do we make a decision now? All right, so there are 2 explanations for why we got a sample proportion as high as 0.669. Either there is really no direction preference and we got 0.669 because of sampling variability, or couples prefer to kiss to the right. So our conclusion here, our probability that our sample proportion was greater than 0.669 was 0. Okay, this is called a p-value. The probability of something happening due to random chance, this is called a p-value. So our p-value was 0. So this means that it is very unlikely. Okay, so my conclusion, since it is extremely unlikely to get a sample proportion of 0.669 p-hat because of sampling variability if the true proportion is 0.5, we can reject the null and conclude that the majority of couples tilt to the right when kissing. Okay, it's very unlikely that because of sampling variability that we got a proportion as high or higher as 0.669. Because of that, we're going to reject the null and conclude that the majority of couples do tilt their head to the right when kissing. The probability that we get when an observed statistic is as or more extreme than the one we observed, assuming the null is true, that's the key, we assume the null is true, is called a p-value. It's a probability. A p-value is a probability. Here there is a 0% chance of getting a sample proportion of at least 0.669 by random chance. In other words, that sample we took was probably a valid sample. Okay. And there should be one more little thing tacked onto the end of this, assuming couples have no preference. Okay, so we assume the null that it's 50-50. People tilt their head to the right or left 50% of the time for each, okay? So, what if the sample proportion was 0.54 instead of 0.669? What would the new p-value be? So, what would be the probability that p hat is greater than 0.54? Well, let's go back and look at our previous data. So the probability that it was greater than 0.54, well, let's see, how many of those? That would be 1 out of 5. So our probability here would be 1 out of 5, or 0.2. So this would be 1 out of 5 were greater than 0.54, or 0.2. So that would be maybe a little bit different. So the probability here would be 20%. So, you know, it is because of that, we would say that I fail to reject the null. So in this case, we would fail to reject the null. So remember, we start by assuming the null hypothesis is true and only reject if we have convincing evidence that the observed results are not due to sampling variability. Okay, so a low p-value means reject the null. A high p-value means fail to reject the null. So how much evidence is necessary for it to be convincing? In other words, how small does the p-value have to be to reject the null hypothesis? So this is something you have to decide in advance. We usually use 0.05 as a boundary, but we could also use 0.10 or 0.01. This value is called the significance level. Okay, just like we decided what level of confidence we had in a confidence interval, we decided that we wanted 90% or 95% or 99% confidence. We have a confidence level decided in advance. We have a significance level decided in advance before we do our null, our hypothesis test. Okay, so in any of these cases, whatever we would have chosen for our kissing example the first time, the 0%, the 0 for our p-value, would have been smaller than any of these significance levels. Our second one, the p-value of 0.2, would have been greater than any of these significance levels. So the significance level is denoted the Greek letter alpha. So we always make a decision. Alpha is whichever one of these we pick. And in general, we reject the null whenever the p-value is less than alpha. So whenever the p-value is small enough to be less than alpha, that's when we reject the null. So our kissing example, our p-value was less than any alpha, and that's why we rejected the null and concluded that more couples prefer to kiss to the right. Most of the time in this course, we do not calculate a p-value by simulation. We use our knowledge from chapter 18, our formulas, and in the kissing example, we start by assuming the null hypothesis is true and p is 0.5. And then what you're going to do is you're going to have some steps. You're going to tell them what you found out and what you're trying to do. You're going to check your conditions. Okay, so our conditions would be 1, that it's a large, let's see, that it's a random sample. 2, that it's less than 10%, our independence condition. And 3rd, that n times p and n times q are both greater than 10. So that's what we check. So we'd have to write like 0.5 times 124 and 0.5 times 124. 62 is obviously greater than 10. So we can apply our formulas. So p hat is then normal with a mean of p and a standard deviation of the square root of p q over n. So then we can say that our p was 0.5. We're always using the true value here. And our standard deviation is 0.5 times 0.5 over 124. So our p hat is approximately normal with a mean of 0.5 and a standard deviation of 0.0449. So now the probability that our p hat is greater than 0.669, our observed value, is equal to p probability, and you can just do NCDF now. You could change it into a z-score. So the probability that z is greater than 0.669, the observed minus the expected 0.5 divided by the standard deviation. So what's the probability that our z-score is greater than 3.76? And you could look that up on your z-table, you'll get 0. The other option here would be to do NCDF, and since this is a normal model, greater than 0.669, so you'd have 0.669 comma infinity, comma your mean is 0.5, and your standard deviation is 0.049449. And if you do that on your calculator, so I'm going to do that here on my calculator. Stat, turn it on first. Stat, let's see, second distribution, normal CDF, and 0.669, infinity, 0.5, and 0.0449. And it gives you this. Now, some of you will look at this and write 8.366. It's actually 0.00008366. It's that. So if you round it like to 4 decimal places, I mean, it's approximately 0, okay, which is approximately 0. So we'll be doing real calculations. So note the value of z is called the test statistic. And it's probably a good idea to start using the z scores again, simply because you can actually see that this value, based on this normal model, that this value of our sample is actually almost 4 standard deviations above the mean. And the probability of that happening should be very, very small by random chance. So the value of z is called the test statistic and tells us how many standard deviations the observed value is from the hypothesized value. When doing a hypothesis test, it is customary to report the value of the test statistic with the p-value. All right, so you do have 4 homework problems to do. Homework number 14, some reading, and 4 homework problems, all odds. So there you go, day 16, second day of notes.